Hi again. We finished the last video with the concept of Moody chart and mentioned that there's certain interesting phenomena happening in terms of pressure drop when you have flow in an axisymmetric pipe. There's a laminar regime below Reynolds numbers around 2000 where the friction factor is inversely proportional with the Reynolds number. When you go to the limit of turbulent flows, you get different solutions and different curves depending on the roughness ratio that you have in the pipe. For all these different roughnesses, one thing that happens and is the same phenomena that happens in all of them is the fact that at large enough Reynolds numbers, the friction factor becomes almost constant. Now, we can gather these ideas and tabulate them, as you guys have seen in the lectures before, in a table like this. We have a column that tells us what's the friction factor and how does it scale with parameter in this problem, for example, that we want to control. Let's say, for example, you're controlling the flow rate and you want to see how friction factor varies with the flow rate. But more importantly, in real engineering applications, you usually think about, for a given flow rate, how much pressure drop you are facing or how much pressure drop you should provide. So the delta P required to have that specific flow rate is something that you want to find whether it's increasing with flow rate linearly. Is it increasing as flow rate to the power of 2 or 5? If you multiply flow rate by a factor of 2, how much extra pressure you need to actually have to drive that flow? And maybe the other parameter that is very important is the power of the pump. Power is force times velocity, if you think about it, because it's the rate at which work is done. So it's force times a length scale divided by time, which will be force times velocity. And it is proportional in this case to nothing other than pressure times volumetric flow rate. Volumetric flow rate is velocity times area. Pressure times area forms force. Force times velocity will give you indeed power. So let's think about the scaling of these things. In the laminar regime, we know that friction factor is going as Reynolds based on diameter to the power of -1. In the turbulent regime, we know that if the pipe has a certain roughness, it's going as Reynolds to the power of 0, which means that in the fully turbulent regime, finally, the friction factor becomes constant. Very smooth turbulent regime, which means that the flow is turbulent, but the pipe is extremely smooth. This doesn't go to a constant. It still decreases with Reynolds, but decreases in a weaker manner than laminar. It decreases as Reynolds to the power of -1/4. This is a result that is given to you from Blasius solution of turbulent boundary layer inside a pipe for the case of 0 roughness. You are not really asked to know it, but if you like to just compare things, I'm writing it on the board so that you see a relatively nice comparison between these different cases. Now, if you think about the delta P, what is delta P? Friction factor is indeed defined as, you can see here, fanning friction factor is defined as delta P over half of rho V squared. So really friction factor has delta P and half of rho V average squared and L over D there. But to really get delta P from friction factor, you see that delta P really becomes proportional to friction factor multiplied to the parameter that you are actually changing. So V average squared comes here. So friction factor times Q squared will finally form what is the dependence of delta P. So often people will think that here, the fact that friction factor is decreasing with Reynolds means that as I go to lower and lower, as I go to larger and larger velocities and increase the Reynolds number, I require less pressure. But that's not true, because friction factor is not only pressure, it's also pressure divided by rho V squared. So as you increase the volumetric flow rate, V, which is exactly linearly proportional to volumetric flow rate, is volumetric flow rate divided by cross-sectional area, is also increasing. So your overall pressure drop will be that friction factor relationship that you have multiplied to V squared, which is F times Q squared. So if in laminar regime you had basically things moving with Reynolds, also we know that Reynolds is by definition rho V d over mu, which is linearly proportional to Q. So if Reynolds is going as Q, F will go as Q to the power of -1. But delta P will go as q to the power of -1 for f multiplied to q2. So that overall dependency will give me something like q1. I really encourage you to do this algebra and feel comfortable with this, because these are the type of questions that as an engineer may actually come to your mind sometimes when you are thinking about designing a system, a hydrodynamic or hydraulic system. And it's very good to know how to juggle these relationships and be comfortable with the power law relationships that you expect. In turbulent regime, however, as you increase the flow rate, Reynolds increases, but the friction factor is not changing. Friction factor remains constant, which tells me that the delta P will go as a constant friction factor multiplied to Q2. So the delta P really goes as Q to the power of 2. However, in turbulent regime, friction factor goes as Reynolds to the power of -1 over -1 over 4, which means that it goes as Q to the power of 1 minus 1 over 4. And multiplied to Q to the power of 2 will give me a relationship for delta P with Q, which is Q to the power of 7 over 4. Now, if I combine these things together for power, here I get that power is delta P times Q. So power increases as Q to the power of 2. Here in turbulent regime is increasing as Q to the power of 2 multiplied to Q, which will be Q to the power of 3. And here for very smooth turbulent regime, it goes as Q to the power of 11 over 4. Now you have a clear idea that indeed why people say it's good to keep the flow in the laminar regime. Because when you are in the laminar regime, as you increase the volumetric flow rate, the power that your pump is required to maintain that flow rate is not going to increase in a Q to the power of 3 manner. It's going to increase in the Q to the power of 2 manner, which is much better than turbulent regime. If in turbulent regime you increase the flow rate by a factor of 2, you need 8 times more power. But here you only need 4 times more power. And again, this comparison between rough turbulent pipes versus smooth turbulent pipes, the second and the third row, will again emphasize to us the fact that if things are kept very smooth, you can still save some money. Not as much as you have saved by keeping things in laminar if you could, but still it's better than rough turbulent pipes. These kind of relationships that you can understand from correct mathematical interpretation of a dimensionless curve like this and bring them to engineering world and in your design ideas that you want to apply to practical designs and problems, these kind of connections are extremely important for a successful engineer in fluid mechanics and hydrodynamics and hydraulics. So I really encourage you to spend time and feel comfortable with this. In Module 2, we really tried many times in different recitations, homeworks, and lectures to show you this connection. And you'd only learn it if you try to juggle terms in your mind and do the math yourself and feel comfortable that you can really understand this kind of power laws and you know the subtleties behind them. Just memorizing numbers is not the goal of this module or course. Knowing the method of thinking and the thought process to get this relationship is what matters, and I hope you will go through it.